Physics students, good afternoon. Mr. Fugit here. In our video today, we're going to be looking at group problem 5b, which covers over uniform circular motion applied to two large objects, the Earth and the International Space Station. So we'll be looking at some of the connections between universal gravitation as well as uniform circular motion. I will not have the copy of the problem pulled up on the screen so that we have a little bit more space to do the work that we need. But if you do need a copy of the problem, remember there is a copy of the problem located on campus as well as a key, or you could also pick up a hard copy in class. I will start by reading the background for us to give us some context of what we're going to do. The International Space Station, ISS, is an artificial satellite in orbit above the Earth. Artificial meaning it's not a naturally occurring object. It has a crew of 6 people on board for months at a time. The ISS moves in a circular orbit around the Earth. It is at an altitude of 400 kilometers, which puts it 6,780,000 meters from the center of the Earth. The mass of the ISS is approximately 450,000 kilograms. The station is in a stable circular orbit above the Earth that we will explore in this problem. Our two primary interests are how fast the station is moving and how long it takes to complete one orbit or period. For reference, the mass of the Earth is 5.97 e to the 24th kilograms. So the first thing the problem is going to ask us to do is to draw a picture. So, just for reference, this will be part A. We have, in a very simple sense, the Earth, and then around the Earth, again, definitely not drawn to scale. We have the International Space Station, which, again, we can represent just with a square, a shape to show that there's an object orbiting around the Earth. Now, part B says this: according to Newton's first law, the ISS should move in a straight line. Right? Objects in motion want to remain in motion unless acted upon by an outside force. So if the ISS is moving, it's going to want to continue moving in a straight line unless there's something pulling it around in a circle. So, what forces might be involved here? Well, think about the forces that we've been looking at this year. Normal forces or contact forces, not going to be there. What's the International Space Station physically touching? Well, nothing. Force of tension, right? No wires or cables. Force of thrust, well, we're not told anything about an engine here with the ISS. Force of friction, no. Force of gravity, that's going to be the one that we're looking at. Remember, a force of gravity is defined as a force of attraction between any two objects with mass. Here, the ISS has a mass. The Earth also has a mass. So those objects are going to be attracted to one another. Now, more specifically, we're looking at the force on the ISS, not really on the Earth. Okay? So here, the way we would draw our free body diagram is this. We have a force on the ISS coming from the Earth. So we would label this as a force of gravity. I'm going to write F sub big G because when we want to find the force of gravity between any two objects and we don't know some of those local constants, the little g values we've been learning about, we need to use our universal approach. And when in doubt, if we're ever unsure about which approach to use, we should know that the big G approach is true everywhere. So if we're unsure about it, we can always use the big G approach. Now, your free body diagram might look a little bit different depending on where you draw the ISS. Right? If you draw it over here, it would be toward the center. If you draw it at the bottom of the circle, it would be up. If you draw it on the right, it would be to the left. The idea is, no matter where the ISS is located around the Earth is going to continue to pull on it, which allows that object to move into a circle. Now, the next part of the problem is this. It's going to ask us to find the actual force of gravity between the ISS and the Earth. So we're given some values in the problem that are going to be helpful. So we'll start with our equation. F sub big G is our constant multiplied by m1 multiplied by m2 divided by d squared, the distance between our objects from center to center. Now, we want to find the actual force. And fortunately for us, we're given most of the other values that we need. So F sub big G is equal to our constant, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. I'm going to go ahead and move this over because I'm going to anticipate I'll need all the space I can get. That is our constant G. M1 and M2 are the masses of our two objects. In this scenario, it's not going to affect us too much, which we call M1, which we call M2. So I'll just plug in the first one. Let's say the satellite is M1. So 450,000 kilograms. And the Earth is M2. 5.97 times 10 to the 24th power kilograms. As we've talked about in class, if you write this as 5.97 E24 or 6.67 E negative 11, that's fine too. The notation can be slightly different, but it represents the same idea. So we have all the values in our numerator, G, M1, and M2. Now we have the value in the denominator, the distance between our objects from center to center. Okay? So that we are told is the 6,780,000 meters. So here we go. 6,780,000 meters squared. But we need to make sure, as we talked about in class, that when we plug this in, we tell our calculator, square the denominator first before dividing. If we don't tell our calculator to do so, it's not going to process that equation properly. So let's take a moment and plug this in. 6.67 multiplied by 10 to the negative 11th power times 450,000 multiplied by 5.97 times 10 to the 24th power, and then we'll divide by our denominator squared. You're going to get a reasonably large value, but again, we have some really big objects here. So the force of gravity between them should probably be pretty substantial. The values that we should come up with look about like this. 3.898. Let me just double check here. And let me put this in one more time just to make sure we're getting the values that we need. Okay, 3.898 times, times 10 to the 6th power newtons. Now, the calculator might give you a value that is not in scientific notation, something like 3.898.102, something in that range. Yeah. But we can write it in scientific notation to shorten things up just a little bit. So now we have the value for the force of gravity between the ISS and the Earth. Now, that isn't the answer to the question we wanted to find. The question we wanted to find was, how fast is the ISS moving, and how long does it take to make one complete orbit around the Earth? But, now that we know our force of gravity, here's a connection that we can make. Our force of gravity, because it is acting toward the center of our circle here, right, the circular orbit, the force of gravity is going to act as our centripetal force. And that's going to be where part D is going to take us. Okay? Part D states this. Because our force of gravity is directed toward the center of our circle, our force of gravity is going to act as our centripetal force. So, we can set our value for F sub G equal to the equation we know for F sub C. Okay? Our force of gravity will act as our centripetal force. And that is going to be kind of a very true relationship when we're dealing with things like planetary motion, or the motion of satellites, or moons around a planet. So now we'll just plug in the values that we know. F sub G we just solved for from part C, 3.898 times 10 to the 7th power, 6th newtons is equal to m. Well, m, remember, that is the mass of the object that's orbiting, because we're looking at the object that's moving in a circle. In our reference frame, in our picture here, it's the ISS that's moving around the Earth. So that's the object that we can describe with our equation for centripetal force. So we're going to use here the mass value for the ISS, 450,000 kilograms. Now we don't know v squared, so we'll leave that value in our equation. We'll divide by the radius, which was 6,780,000 meters. Okay, so now we have, looks like most all the values that we need. Let's see if we can move this over just a little bit. Oh, come on now. Let's see. There we go. Now, I need to get rid of a few values, right, to get v by itself. So I'm going to multiply our radius of our circle, which again, the total radius of our circle, think back to our picture, is the distance from the center of our circle all the way out to the edge of our circle, which again is the distance from the center of the earth out to the ISS. So the radius of our circle is the distance between the objects. So if I multiply that value up to the numerator, I have to do the same over here. So I'm going to rewrite this a little bit. So I've got 3.898 times 10 to the 6 newtons multiplied by 6,780,000 meters. So I multiply it up on both sides. So I'm kind of rewriting this so that we have enough space. So I'll cancel out my distance between objects, or the radius. And then I need to divide the 450,000 over. So I'll divide 450,000 kilograms to the other side of my equation. So divided by 450,000 kilograms. So you can see that step. So 450,000 over 450,000, okay, will simplify down to 1. And this is equal to v squared. So now we have an equation that we can use to solve for velocity. I'm going to take all these values and I'm going to multiply, divide them so we can get them down to one value. So we'll take our force multiplied by the radius of our big circle here, divided by the mass of our object here, the ISS, and then we're going to eventually take a square root. So here, once we resolve these values into one number, so multiply the numerator, divide by the denominator, we get a value of approximately v squared equal to, looks like 58, a little long, 731415. Again, it's not really important that you write that value down. If you could just go ahead and take a square root, but it is important that we see that's not the final answer, right? So we take a square root and we get 7,663. Seems a little bit more reasonable here. And that is a velocity, so meters per second. Now, one of the nice things about our values is that for the ISS, we can actually look these up and double check these. If you were to go to Wikipedia, you would see a value provided for the ISS of about 7.66, and it will say km per s, meaning kilometers per second. So if we do some mathematical converting here, convert kilometers to meters, the value that Wikipedia would give us, 7,660 meters per second. Which tells us that the work we're doing, the equations that we're using, are a valid way to analyze the motion of our space station. Now, the last part of our question is going to ask us to find the time. This is going to come in part F. Now, the only equation we've dealt with involving time, or period, for an object moving in a circle looks like this. The velocity of our object is equal to the circumference, or the distance it travels around its circular path, divided by the period, t. Now, we want to find what t is equal to. However, the equation we have isn't set up to give us that answer directly. So, before we plug in any values, one thing we can do is this. I'm going to multiply t to the numerator of my equation. So, t over t, those values will cancel out. And then next, I'm going to divide my velocity term over so that I can get t by itself. And now I have an equation that's set up to give me the period. The period is 2 pi r divided by the velocity. So now we can use our equation for period, velocity, circumference, and to find the period directly. So here we go. Our circumference, 2 pi times the, again, radius of our big circle here that we're making, 6,780,000 meters. divided by our velocity, what we just found, the 7,663 meters per second. So now we can plug these values in. We'll go 2 pi multiplied by 6,780,000 divided by 7,663. Now we're going to get a number that looks pretty large. T, we should see, is equal to approximately 5,559, but that's a time value, so we have to be careful with the unit. Look at your equation. The numerator we have meters, the denominator we have meters per second, which tells us the standard unit that we should be getting out of this equation for time is in seconds. So this would be 5,559 seconds. Now, it's a really big number for a time value in seconds, so that's kind of hard for us to understand or make reference to. But what we can do is this. I can actually convert that time to maybe minutes, so that I have a little bit of a better idea of how long that is. So seconds to minutes, factor of 60. I can divide my answer by 60. I get about 92.6 minutes. I can also convert this to hours by dividing by 60 again. This would be approximately 1.54 hours. So those values seem to land a little bit better, meaning we kind of have a better idea or a frame of reference for 92 minutes or an hour and a half. Now, if you look up these values on Wikipedia, or any other trusty, reliable internet source that you choose to use, you're going to see what is called orbital period, the period of one complete orbit, as right about 92 minutes, which is extremely close to the values that we're finding using our equations. So again, we have a way to validate the numbers that we're coming up with. So, hopefully this gets us going in the right direction, looking at group problem 5b, using our equations for universal gravitation, and then showing how they're applicable and connected to the ideas of circular motion and objects in orbit. As always, if you have questions, don't hesitate to ask. Good luck.